In this lecture, we will introduce the frequency response of a circuit, which is a very important subject from the signal processing point of view. And it all has to do with the transfer function of a circuit. Okay, so suppose that we have an LTI circuit, okay, with some input and some output of interest, input, and this is the output. Okay, input being W of t in time domain, and its Laplace transform is denoted by W of s, and y is our output. Okay, and suppose that this circuit from this input to that output can be described by some transfer function, which we denote by h of s. Okay, so h of s is the transfer function of our circuit. Therefore, y of s, the output transform, equals h of s times the input transform. Now, if the circuit is stable, we can talk about a sinusoidal steady state, okay, when the input is some sinusoidal function, and we have in our previous lecture, we have studied the relation of the transfer function to that sinusoidal steady state response. Okay, in particular, we have figured out the following. Okay, suppose that this is the input and here this is the output. If the input is the following sinusoidal function, okay, with amplitude A, frequency of oscillations being omega radians per second, and some phase which we denote by phi, then in steady state at the output we measure or we find the following signal. So first of all, since the circuit is LTI, at the output in sinusoidal steady state we will see again a sinusoidal signal that's oscillating at the same frequency, okay, with the input. That is the frequency of oscillations for the output will be omega. Now, how about the amplitude and phase of the output? We've seen that they can be they are directly related to the transfer function. In particular, the amplitude of oscillations at the output is such that it equals the amplitude of the input times the magnitude of the transfer function evaluated at s equals j omega, omega being the frequency of oscillations. Okay, a very important relation between the transfer function and the sinusoidal steady state response. As for the phase, okay, again, phase of the output, again it can be computed easily by the transfer function. The phase of the output was such that it equals the phase of the input, okay, plus the phase of the transfer function evaluated at, again, s equals j omega. That means at the output for this input we can write for a stable circuit the following: HA times h j omega magnitude, and then we have cosine omega t. The frequency of oscillations is directly inherited from the frequency of the input. Okay, and as for the phase, it's phase of the input plus some extra phase coming from the phase of the transfer function. Okay, plus the phase of the transfer function evaluated at s equals j omega. Okay, so this is what we expect at the output in steady state. Okay. Okay, so this is very, very important. Therefore, let's put down those three important things that we have just talked about. Okay, that is the output signal's amplitude, or the output magnitude, equals the input signal's magnitude times a factor, okay, and that factor is the magnitude of hj omega times hj omega. As for the phase of the output phase equals, so by output phase we're talking about this quantity here. Output phase equals input phase plus the phase of the transfer function evaluated at s equals j omega, and once again omega is the frequency of the oscillations of the driving force of the input, okay, and the output frequency equals input frequency, okay, so both are omega radians per second. Now this observation makes it clear that these things are very important, the magnitude of hj omega and the phase of hj omega with respect to the input frequency, okay. So that motivates us to study that pair, the magnitude of hj omega and the phase of hj omega with respect to the frequency of input, frequency of oscillations of the input function, okay. So the gain function, or by gain function we mean this magnitude, okay, the function of the magnitude of the transfer function with respect to omega, and as for the phase function we mean the phase of the transfer function evaluated at s equals j omega. Sometimes this is indicated by theta of omega, okay, and together this pair, so here we have two functions, okay, one is the function, both are the functions of omega, the input frequency, and one is the gain function, the other is the phase function, and this pair of functions is what we're calling the frequency response of a circuit or of a transfer function. Okay, these two functions define the so-called frequency response of the circuit. Okay, so together, if you know both of those functions, which we can compute, provided that we have access to the transfer function, together they completely characterize the relation between the input and output when the input is a sinusoidal function, okay, in steady state. For instance, consider the following example, a qualitative example. Suppose that omega h omega. So suppose the gain function has the following plot, okay, h omega with respect to omega. This is 0, and what we have is, suppose it's something like that. So what does this shape mean? Okay, first of all, the magnitude of h omega, okay, or the gain function, is significant in the following sense, okay? It describes how the amplitude of the input, okay, is shaped to produce the magnitude or the amplitude of the output, okay? So this means that at low frequencies, h omega is near 0. So that means at low frequencies, when the input is, the input oscillations are low, so that means at the output we don't see much of a signal, okay? The amplitude of the signal will be tiny. And at the other tail, that is, if the input frequency is very large, okay, if omega is high, then again, since the magnitude or the gain function takes very little low values for high frequencies, high omega, so that means again for high frequency input we don't see much at the other end, at the output end. And somewhere in between, let's say at intermediate frequencies, when omega is somewhere here, the gain function takes some meaningful values, okay? And then, so that means when the frequency of the input is somewhere in this range, then at the output we see some significant signal, okay? So let's try to visualize that rough explanation. So this implies the following. Suppose that this is our circuit. This is the input side, this is the output side. Now we're going to consider 3 cases. And here again we have the same circuit. H of S. Okay? Now suppose that here, okay, this represents the input signal, and the frequency of this signal, suppose it's somewhere here, okay, omega equals, let's say, 10 Hertz. And then at the output, since the gain function for those low frequencies is not, it takes a very little values, so that means at the output, since the output magnitude is input magnitude times the gain function, h omega magnitude, and since h omega magnitude for low frequencies is small, so that means we're going to see, yes, a sinusoidal signal with the same frequency of the input, but its amplitude will be significantly smaller than the amplitude of the input signal. So for instance, we're going to see something like this. Okay. And then at the other tail, okay, suppose that we're talking about frequencies at here, okay, and the input we apply is oscillating at those frequencies somewhere here, okay, and then again for those high frequencies the gain h omega, the gain function, takes very small values, so that means at the output still, okay, we're going to see something with the same frequency as the input, but the magnitude of the output will be significantly smaller compared to the magnitude of the input. So that means here we're going to see something like this. Okay, a sinusoidal with very little amplitude, okay? And somewhere in between, let's say for frequency omega, that falls into this range, okay? Okay, so here we have something like this, let's say. Then, because for that frequencies, the gain function takes some meaningful values, some not so tiny values. So at at the output for those frequencies, we'll see something significant. Okay. Okay. So this is a qualitative example that makes us see what the gain function means from the input-output amplitude point of view. Okay. Now let's introduce some definitions associated to the frequency response. Okay, some definitions. Okay, here is our first definition. Stopband, the range of frequencies over which the output is significantly attenuated. Okay. So for this case, for instance, this would be part of stopband, and also this frequency range would be part of the stopband. Okay. And passband is what remains when you take the stopband out of the range of all possible frequencies. Okay, so it's the frequency range over which there is little attenuation. Okay, or perhaps amplification. Okay, so that's what how passband is defined, and then the border frequency or frequencies that separates stopband from passband are called cutoff frequencies. Okay, cutoff frequency. The frequency associated with the boundary between a passband and an adjacent, okay, or a neighboring stopband. Usually, cutoff frequency omega sub c, okay, omega c is the frequency satisfying hj omega c equals 1 over square root of 2 times the maximum gain that the gain function attains, okay, times max omega of h omega, okay. And sometimes this frequency is called the half power due to this 1 over square root of 2 thing. It's called the half power frequency. And finally, bandwidth is the frequency range spanned by its passband. Now let's apply or try to visualize these definitions over a simple gain plot. Okay. And the pair of plots, gain plot and the phase plot, together they're called the frequency response plots. Okay, so suppose that this is our gain function, okay, magnitude of h omega with respect to omega. Okay, and suppose that it has the following shape. It starts from, okay, let's say some k, and then it decreases monotonically and it becomes smaller and smaller as the frequency increases and it approaches to infinity. Okay, this is 0. Now the maximum value of the gain for this shape is the value that it takes at omega equals 0. Okay, so it's so-called the DC gain is highest for this example, and then as the frequency increases it becomes smaller and smaller. So the maximum gain is k, so k divided by square root of 2 is somewhere here, let's say, okay, k over square root of 2, and then you figure out the frequency corresponding to that value of the gain. Okay, and that frequency is what we're defining here or introducing here as the cutoff frequency. Okay, so this therefore is the cutoff frequency for this gain characteristics. Okay, and now having figured out the cutoff frequency, we can easily determine what's stop band and what's pass band. So cutoff frequency is the frequency that marks the border between stop band and pass band. So in this shape it's clear that this is stop band because this is the tail part, and in the tail part the gain is very much smaller than the first part, okay, from 0 to omega c. Therefore this here is our stop band. Okay, that is frequency start from omega c up to infinity. Okay, so that range is our stop band for this gain characteristics, and from the frequencies from 0 to omega c, they are our pass band for this filter. Okay, and as for the bandwidth, bandwidth is the length of the pass band, and in this case the bandwidth is omega c minus 0, it's omega c, so that's the bandwidth for this gain characteristics. Okay, now in this course we'll be studying 4 types of gain characteristics. Okay, so let's introduce those 4 types. Prototype. Okay. Prototype gain characteristics. Okay, we'll be studying namely low pass, high pass, band pass, and band stop filters, okay, or types. This is what we call the low pass. For the sake of completeness, let me redraw it here. Omega. Okay. The shape has the following picture. For the low frequencies, pass to the other side, okay, we see at the output. And as for high frequencies, even though we have some significant input at the output, we don't see much, okay. Since the low frequencies, in a sense, are allowed to pass to the output side, such characteristics are called low pass characteristics, okay. So here the type is low pass. And suppose this is 0. Somewhere here we're going to have the cutoff frequency, omega c. So here this is passband, and here we have the stopband, okay? The frequencies from 0 to omega c, they make our passband frequencies, and frequencies from omega c to infinity, they make the stopband frequencies. And as for the bandwidth, okay, the bandwidth is the length of the passband range, and in this case it's omega c minus 0, it's omega c. The bandwidth equals omega c. Okay. And this type is, once again, is called low pass, because the low frequencies are allowed to pass to the other side. And then here is our next prototype. Which has the, in a sense, the reverse shape from 0. Again, we're talking about the gain, omega. Okay, so suppose that the maximum gain is attained at very, very large frequencies, let's say when omega tends to infinity. Therefore, the cutoff frequency will be somewhere here. Okay, and then in this case, the frequencies from 0 to omega c will be, since the gain is significantly smaller here in this range from 0 to omega c. So that means for frequencies from 0 to omega c of the input, we don't see much at the output, okay? Whereas for the frequencies that are larger than omega c, the gain is significantly higher, and then the input, in a sense, is transferred to the output in a significant sense. Therefore, this part is our stop band, and from omega c up to infinity, we have the pass band. Okay. Since the high frequencies are allowed to be seen at the output side or passed to the other side, this type is called the high pass filter. Okay, so this is a high pass filter. Okay. As for the bandwidth, bandwidth is the length of the pass band. In this case, since the range is from omega c to infinity, the length of that interval is infinity minus omega c is infinity. Okay, so bandwidth is infinity. Okay, now there are slightly more sophisticated gain characteristics. Or more selective, let's say. Here's another type that we will study. Okay, it has this bump shape, gain omega. So the maximum is somewhere here, and then to figure out the cutoff frequency, what we do is we multiply or we scale that maximum value with 1 over square root of 2, and we figure out the corresponding frequencies, and those frequencies, they make our so-called cutoff frequencies. In this case, if this is the max point, then that would produce 2 cutoff frequencies. Okay, one is here, the other is here. Let's call them omega c1 and omega c2. Okay, these are the cutoff frequencies, and then once the cutoff frequencies are determined, it's clear where is the passband and where the stop bands are. So here we have first piece of our stop band. This frequencies from omega C2 to infinity. They also make our stop band, and the range between omega C1 and omega C2. Okay, so the window between two cutoff frequencies, it makes our passband. Okay, for this case. Okay, now since only a range of frequencies, okay, from some frequency omega C1 to omega C2 are allowed to pass to the other side in a significant sense, this type of gain characteristics are called band pass characteristics, okay, or band pass filter characteristics. So this is what we call a band pass gain characteristics. And as for the bandwidth is the length of the passband window. In this case, it's omega C1 minus, omega C2 minus omega C1. Okay. Omega C2 minus omega C1. And finally, we have, in a sense, the reverse shape. Okay, something like that. Omega C1, omega C2. This is our gain plot. This shape, this shape of the gain function makes it clear that the frequencies from omega C1 to omega C2 in this range, somewhere in the namely the intermediate frequencies, so to speak, are not allowed to pass to the other side. Okay, well, something passes to the other side, but it's not much compared to the very low frequencies and very high frequencies. Therefore, this type is called band stop. Okay, where a certain band, in this case it's from omega C1 to omega C2, is not allowed to pass to the output side, whereas anything that's outside that band can be observed or measured at the output side. Okay, so here we have passband, and this is also part of our passband, and in between we have the stop band window. Okay, and this is called band stop. And the bandwidth of the band stop filter is the length of this interval, the passband interval, and plus the length of this interval. Since the second passband interval is, or the second piece of the passband interval is of length infinity, therefore the bandwidth of such filter is set to equal to infinity.